I want to go over that derivation for boundary shear stress that we did in class the other day. So here is a drawing of kind of a cross-section view through a river. This is the bed of the river. This is the water surface here that has some slope to it. If there wasn't a slope, the river wouldn't flow. And it slopes at some angle alpha, okay? Or some slope, rise over run. What we're interested in, recall, is finding the force that's acting to erode the bed, which we call the boundary shear stress, tau naught. So that's the force that we're trying to find, and that's what we're interested in, and what controls that force. Now that's a stress, so that's applied over an area. Force applied over an area is called a stress. So we have to think, what are the properties of the water? Slightly different way of thinking about this. The properties of this water in this diagram, right? Well, one, it has some water depth, d, right? And then the water has a density, rho, which has dimensions of mass over length cubed. And then we have gravity acting on that mass to drive the flow, which has dimensions of length over time squared. That's an acceleration term right there. So these are the things that are tending to drive the flow: the density, the gravity, and the depth of the water. And then clearly it depends on this slope here, all right? But expressed more how I did in class, we were interested in what's going on right here on the bed, right? We know that acting down toward the center of the earth, like this, is the weight of the water, which in this case equals rho g d, right? We use d instead of a volume because we're looking at the weight per square meter, right? So essentially it's at an instantaneous point, all right? And if we were to just look at the dimensions of that, we can play this game of going mass over length cubed for density, length over time squared for gravity, and length, like that, for depth. And we can figure out the dimensions of weight because of cancellation, right? That's going to cancel with one of those. Boom, boom. And we're going to get mass over length times time squared. Okay? So those are my dimensions of length, or dimensions of weight. And that's what's acting down toward the center of the earth to drive this flow. We now look at the two components of this, and one of them is the component acting perpendicular to the bed, which is tending to keep the water on the bed, which is good. And then there's this one working parallel to the bed, which, as you would recognize, is just like our tau naught, right? Which is our tau naught. Okay, so that's the component that's acting parallel to the bed. And so we can play the SOHCAHTOA game, and we can flip that triangle on its side. It's a nice little right triangle. Well, that triangle sucked. Let's make it a little bit better, hopefully. Right, so I've just flipped this triangle here. Here's the right triangle on its side. And this, we know, we want tau naught, right? We're going to know alpha, and we're going to know the weight. So this is a case where we know that so tau naught equals the opposite side, and W equals the hypotenuse. So we know that the sine, right, of alpha equals the opposite over the hypotenuse, which means it equals tau naught over the weight, right? So we just rearrange to solve for tau naught, and we get tau naught equals the weight times the sine of alpha, and expanded, that equals rho g d sine alpha, okay? Now there's that special case, no, I shouldn't say special case, but for very low alpha, the sine of alpha equals the tangent, approximately equals the tangent of alpha, and the tangent of alpha uh, is just rise over run, and that equals the slope, s. So we can actually rewrite our equation as tau naught equals rho g ds for the slope, rise over run. And sometimes, because rho and g don't vary on Earth very much, gravity stays about the same, density of water stays about the same. This is sometimes written as rho g is called gamma, which is what we call the specific weight of water. And you can have a specific weight of water, you can have a specific weight of a sediment, like a sand grain, but it would be gamma ds. So we can essentially simplify that whole thing down to that. So that's basically what I covered in class.